In today's video, I'll be talking about something really useful if you're working with data in Python, and that's NumPy. It stands for Numerical Python, and it's this amazing open source library that makes dealing with numbers super easy, fast, and efficient. Basically, NumPy lets you work with arrays, which are kind of like Python lists. Now, you guys must be wondering, if Python already has lists, why do we even need something like NumPy? I mean, lists let us store numbers, loop through them, do calculations, and get things done. But while lists are great, NumPy overtake lists in terms of performance, memory, and overall convenience. Let us quickly see how. So before we proceed with looking at how NumPy arrays perform better than Python lists, let me tell you that I have written some codes that include the NumPy syntax as well. But you guys need not worry about it right now because I'll be covering each and everything in detail step by step. So starting with the very first difference is speed. Okay. So consider a scenario where we have a list, and what I'm going to do is I'm going to multiply this with a really large number. So what this basically means is 1, 2, 3, 4 is repeated these many times in this particular list. Alright. So now what I want to do is I want to multiply each and every element of my list with the number 2. Alright. So basically after the multiplication, what my list is going to look like is 2, 4, 6, 8, and then again 2, 4, 6, 8, basically 10,000 times. Alright. So this is what I want my final list to look like. Now in order to implement this particular logic, what I will have to do is I will have to loop through my entire list and manually multiply each and every element with 2. Alright. Since I want to multiply it with the number 2. Now, this process is going to take some amount of time, right? And in order to calculate that time, I have written down some code for you guys. So over here, as you can see, I have imported the libraries, NumPy and time. Now, if you guys try to import the NumPy library directly, there is a high chance that you guys will get an error. So do not worry about it right now because I will be telling you how to install it in your systems as well. So here you can see I have created my list and I have written my start time over here, and I have created a for loop where I am multiplying each and every element of my list with the number 2, and then finally I'm printing the amount of time that was required to perform this particular operation. Alright, so you can see over here it's around 1.13. Now if I do the same operation on a NumPy array, over here you can see I have created np.array. Do not worry, we'll be discussing it later. So you can see the time taken for a NumPy array is just 0.03. Alright, so this is a huge difference. Now if you guys are wondering why there is such a huge difference between the speed of NumPy arrays and the Python list, let me tell you, NumPy is built on C. Now C is a low level language. Okay, so whatever operations the C language performs are much faster compared to Python. Alright, so coming on to our next point, which is memory. Now NumPy is considered more memory efficient. Okay, now why is that? Let's quickly look at an example and understand it. So now in order to check the memory usage of Python lists and NumPy arrays, I have imported sys library, and this is my Python list and here is my NumPy array. Alright, so over here I'm going to get the size of my list, and over here I'm going to get the size of my array. Now if I run this, as you can see over here, my list size is 104 for these 5 elements and my array size is 40, again for these 5 elements. So this is why NumPy arrays are considered more memory efficient as compared to Python lists. Okay, so far we have discussed speed and memory. Now another point is direct operation in NumPy arrays. Alright, so when we were discussing the code for speed difference between Python lists and NumPy arrays, you guys must have noticed that to perform the same operation on Python list, we had to write a for loop. Whereas in a NumPy array, all we had to do was write a one-line code, right? So this is another property of NumPy array, which is called direct operation, which is also known as vectorization. Alright, so let me just write it down over here. Okay. Okay, so as you can see over here, I have listed down some basic differences between Python lists and NumPy arrays. The first one is speed, which we have already discussed. So Python lists are slower compared to NumPy arrays, which is mainly because NumPy arrays are based on language C or built on language C. Alright. Then we have data types. So Python list basically allows mixed data types. Alright. So you can create an array which has a number and say a letter, and then you can also have a string. And apart from that, you can also have a float. Alright. And your list is going to work absolutely fine. But in case of a NumPy array, what's going to happen is all the elements are going to be converted to a string format. So let's quickly go ahead and check it out on our notebook. Alright, so let me create a list having different data types. So, alright. Now if I were to create an array and store it in a variable called ARR, so you can see all the data types over here, being an integer, being a float, are converted into a string type, right? Because NumPy allows only same data type to be stored in a particular array. So the next one is memory efficient. So Python lists are comparatively less memory efficient as compared to NumPy array. We have already seen this. Then comes mathematical operations. So if you want to perform any sort of mathematical operations on our Python list, we will have to manually loop through them and then implement the operation on each element separately. Whereas NumPy arrays have something known as direct operations, which is also known as vectorization. Alright, so this is a very important property of NumPy arrays. Moving on to built-in functions. So Python lists have very limited built-in functions, whereas NumPy arrays have a lot of powerful tools, which we'll be looking into shortly. Alright. So let's get started with NumPy. So the very first thing you need to do is open any command prompt. It could be your terminal, it could be your normal command prompt. And all you have to do is run the command pip install NumPy. Okay. And when you run it, your NumPy library is going to get installed if it is not installed already. So once you have run the pip command to install NumPy on your systems, you can go to any notebook. I'm using Google Colab. You can use VS Code or Anaconda, Jupyter Notebook, any platform. And the first step that you need to perform is import the library that you have installed, saying import NumPy. Now you can leave it at that, import NumPy, but there's a common practice of using as NP, where as NP is nothing but your alias. So generally we import NumPy as NP, and then whenever we have to use the library, we just say NP dot. Okay, we just use NP instead of NumPy. So the very first basic step is creating a NumPy array. So first we'll be looking at the inbuilt functions, and then we'll see how we can create those arrays manually using np.array function. So we can just pass a list in that array. Okay, let me just go ahead and quickly create an array, np.array. Okay. So we'll be looking at the properties and how we can implement this in detail in the later stages. But before that, I want to make a few concepts clear for you guys, like dimensions and shape of an array. Okay. So this is somewhere most people face confusion and doubts. So let us go ahead and resolve this query first. Okay. So when we have a single number, this is basically something known as scalar, and it is going to have 0 dimensions. Okay. Now, if I have data that is spread across one direction, that is, if say I have 1, 2, and 3, now this is going to have a one dimension. Okay. But if I have data that is spread across rows and columns, that is in somewhat this way, maybe 1, 2, 3, and 4, 5, 6, this is known as two-dimensional. Okay. So let us go ahead and check this. So if I were to check the dimension of my array that I just created, I will have to store it in a variable. Okay. And so now let me go ahead and, okay. So you can see the dimension of my array is 1 over here. But if my array looks something like, so you can see my dimension for this particular scalar element, scalar value is 0. Okay. Now, brackets in NumPy play a very important and major role. So whenever we're defining dimensions, we'll be creating arrays in the later stages. So I'm just going to give you a theoretical overview. So is basically if we have a single bracket and elements inside it, it is going to be a one dimension. Okay. If we have two brackets, so this is going to be two dimensional. Okay. As the number of brackets increase, so do our dimensions. Okay, let us quickly go and check it. Okay, so let me just create empty arrays. Let me just initialize the arrays using brackets. Okay, so that you guys get a more clear idea. And I'm going to pass a single bracket. And then I'm going to check the dimension of my array. So it is the dimension is checked using this function ndim. Okay, so this is an inbuilt function. You just have to remember the syntax, that is ndim. Okay. Okay, so there are no brackets over here. It's just ndim. Okay, so you can see there's one bracket and there's one dimension. If I increase the number of brackets here, okay, now let's run it. So my dimension is 2 now. Now if I further increase my brackets, the dimension is 3. I can add the brackets anywhere. Okay, it does not matter. Now my dimension is 4. Okay, so now it's up to you how you are defining the array, how you are, what's the shape of your array. Now, if I go ahead and check the shape of my array, shape is nothing but that tells us the number of rows, the number of columns. Now, over here, our dimension is 4, so we are going to have data spread across 4 particular rows, right? So, it's basically going to be a 4-dimensional space. So a 3D object looks like this, right? We had created this. So this is a 3-dimensional space. A 4-dimensional space would look something a little more different, a little more complex to draw right now. So basically, this is how it's implemented. Now we'll move on to creating arrays using the inbuilt functions. Like the first one is going to be range. So basically, whenever we have a list, okay, say I want to create a list containing elements 0 to 10. How would I do that? I can either manually write all the numbers like 0, 1, 2 and so on, right, till 10. Or I can go ahead and create a for loop. So I will say for I in range 10, and then I will just L dot append, okay, and I will insert my array. Okay, so this is what I would do for a list. But in order to avoid all these complex operations, I can directly go ahead and say np dot arrange, pass the range, that is 0 to 10, and by default my step value is going to be 1, so I will not write anything and I just have to store it. Okay, so let's go ahead and see the practical demonstration or the hands-on demonstration of all these functions in our Google Colab notebook. All right. So the very first thing we're going to do is try to create a range of numbers, like a Python range. So let's say I want to create a range of numbers between 1 to 10. All right. And let's store it in a variable called range. So as you can see over here, I have a NumPy array with the elements 1 to 9. All right. So the last element, which is our stop element, is not included. And just like Python, we can also provide a step value. So say if I want to skip one value, so this is what my NumPy array is going to look like. Alright, so this is basically the start. Let me just write it down here. Start, stop, and the step value. Alright, so the start value is included, the stop value is never included, and the step value is basically telling us how many numbers to jump. Okay, by default it is 1. Alright. So moving on to the next property of NumPy, it's called linspace. Alright, so this helps us create evenly spaced numbers. Alright, so say if I want to create an array with a specific number of values which are evenly spaced between two numbers. So say I want to create, so let's create an array np.linspace, and I want to create numbers or values between 0 and 1, and I want 5 values between them. Alright, so let me print it as well. So see, I have values between 0 and 1 and they are evenly spaced, right? So 0, 0 0.25, 0 0.5, 0 0.75 and then 1. Alright, so if I were to say I want 10 values, this is what my array would look like. Clear? So basically over here, we are giving the parameters of start, stop and number of values between them. Alright. So this was all about linspace. Moving on to the next property of NumPy array. So these are basically the inbuilt functions, alright? We can create different types of arrays using a range, linspace, and the next one that we have is log space. So the name itself suggests that this is something related to the log, right? So this is nothing but a logarithmic scale array, correct? So let me again store it in ARR itself. Okay, and I want my array to start from 10 to the power 1 and end at 10 to the power 3. And I want 3 points only. Alright. So basically what I'm telling here is 10 to the power 1 to 10 to the power 3. And how many values I want between these? Basically I want 3 points. Sorry. Not the number of values, the number of points. Okay. So let me just print. Yeah. So 10 to the power 1, 10 to the power 2 and 10 to the power 3. Alright, I'm getting 3 points. Now if I were to say I want 2 points over here, let me see how it would look like. So I would get only 2 values. Alright. So np.log space, let me just make it more clear for you guys. It's basically taking the starting, or you can say the starting power value, okay, the ending power value. Over here the start end are the powers, alright, these are the powers, and then our last parameter is going to be how evenly spaced you want the scale to be. So if I want 3 points on the scale, I'm going to get 3 values. If I want 2 points on my scale, I'm going to get 2 values, alright. So this is basically going to tell us the number of values again, alright. So I hope this was clear. So moving on to the next property, which is np.zeros. Now what this is going to do is it is going to create an array full of zeros. Alright. So let's see how this is implemented. Okay. So let's say I want an array called ARR, which is full of zeros. So I can directly go ahead and create mp.zeros 5. Now what this 5 here is, it is going to tell me how many number of zeros I want in my array. So basically the size of my array is going to be 5. Alright, so let's print it here. Now this is basically just one line of elements, right? Okay, so another great use of NumPy arrays is that they are used for creating a matrix, which is nothing but rows and columns. Alright. So if I want to create an array which is full of zeros, but I want 2 rows and 3 columns of these zeros. So this is what I'm going to do. Alright. So basically over here I have 2 rows and 3 columns. Okay. So as you can see over here, these are my 2 rows. This is my row 1. This is my row 2. This is my column 1. This is my column 2. And this is my column 3. Alright. So when I defined in the np.zeros parameter 2, 3, what I meant was 2 rows and 3 columns. Alright. So you can create 2D, 3D, 4D, any number of dimensional arrays using NumPy. Alright. Say if I were to say 5, I'm giving random dimensions over here. So here, this is how my array would look like. Alright. So NumPy is never going to raise an error. How many dimensions you want, you can give the parameter over here. For now, we'll just keep it limited to 2, 3, which is practical enough, right? So similar to np.zeros, we have another NumPy property, which is np.ones. So you guys must have gotten a basic idea. Similar to np.zeros, we have np.ones, which is basically nothing but instead of zeros, we're going to have ones in our array. Alright. So whenever we want to create an array where all the values are 1, we can use this particular function. So I'm going to create an array having the dimension of 4, 2. Alright. And I can also decide a data type. Alright. So if I want to give a data type over here, okay, and I want my data type to be an integer, so here you can see. But if I do not write this particular argument or parameter, by default my array is going to be a float. as you could see over here as well. Alright, so we can write, let me just comment. Similarly, this is something array full of, alright. So previously we saw how we could create an array which was full of zeros or ones. But now we can create an array having a value of our choice. Okay. So now over here, similarly, what we were doing earlier, maybe I want to create an array having 10 elements and my default value is going to be 2. Alright. So instead of NP, I wrote ARR by mistake. So that's why I was getting the error. So let's print it here. So I have 10 values of 2. Alright. Now if I want to create a 2D array, I would simply say np.full and I would pass the dimensions say 2, 4, and I would have to pass this in a square bracket because I also want to pass a default value which is going to be 7 in this case. So my code looks neat and it's easy to understand also right now. Alright. So if I print it here, I have 2, 4, so 2 rows and 4 columns of the default value 7. I can pass another value here, maybe 7.1. Yep, so 7.1, no error, smooth and easy. Alright, so let me just write it down to you guys. So it takes the parameters of row, column and a default value. Alright, so moving on to the next function is np.empty. So this is basically an uninitialized array. Okay, so whenever you want to create an array without setting any sort of values, so you can simply use np.empty. Alright, so let me store it in a variable called arr again. You guys can go ahead and create different variables, but I'm too lazy to do that, so I'm just going to use arr over and over. So over here in my empty brackets, I'm simply going to pass the dimensions, which is 2, 3. Alright, so let me just print it. So basically it's an uninitialized array. This is not np.zeros. This is an uninitialized array. Okay, basically there are no elements over here. So this method is basically faster, but it's not safe unless you're going to override these particular values. Alright. So whenever you want to override these values later on in the later stages, this method is pretty good to go because it's really fast. Alright. So moving on to the next function, which is np.random.rand. Now this function is going to generate random floats. Now floats are basically going to range from 0 to 1. Alright. So, and these are going to be uniformly distributed. Alright. So I just have to pass my dimensions. Say I want to generate 10 random floats between 0 to 1. Let me print it as well here. So I have 10 random floats between 0 and 1. Okay, and they're going to be uniformly distributed. Let me try another one using np.random.rand and my dimensions are going to be 2, 3. Okay, so this square brackets is not required over here because instead of dimensions, the np.random.rand function is considering it as a list. So make sure you pass these dimensions without any square brackets, okay? Since it's not taking any default value or no third parameter, we are not going to use square brackets for these particular dimensions here. Alright, so here I have 2 rows and 3 columns, as you can see. 3 columns and 2 rows. Alright, so this was np.random.rand. Moving on to our next function, which is np.random.randn. Okay, now randn basically stands for random numbers having a normal distribution. Yeah, so Google Colabs has generated the definition for us. So basically these are the random floats from standard normal distribution. Okay, what this means is that this particular function is going to generate values from a standard normal distribution, meaning the mean is always going to be 0, mean is nothing but the average, and the standard deviation is always going to be 1. I'm sure you guys are familiar with a graph like this. Okay, so the mean is somewhere over here, which is basically 0, and our standard deviation, which is basically telling us how spread our data, is always going to be 1. Alright? This is also known as the graph for normal distribution. Okay. So in order to generate random numbers having a normal distribution, all you have to do is pass the dimension again. So I'm just going to go for 2 comma 3, and then I'm going to, okay, I haven't stored it in a variable. Let me just store it, and then I'm going to print add. So here my values are also going to be negative because again they're normally distributed, and the center is going to be 0. Alright. Then the next one that we have is nb.random. Random basically stands for random numbers. I hope you guys got an idea about that. Okay. Dot randit. Now this is the most simple one so far. This is basically just random integers. Okay. So here we are going to generate random integers within a particular range. So over here what we are going to pass is the starting value, the stop value, and the size. So I want it in a size, and if I don't mention the size, I'm by default going to get 1 row. Okay. So let me just run this. I haven't printed ARR. Okay. So I got one random integer called 99. Okay. So I did not specify how many integers I want. I just gave a range that I want my random integer to be between 10 and 100. Okay. So it is going to be start, stop, dimension, or the number of values. Okay. So if I were to run this again, having a different kind of parameter, okay, let me just do it. So now I'm going to give a dimension of say or size 2 comma 3. So here I have 2 rows and 3 columns. So basically 2 comma 3 means I'm going to have 6 random integers in my NumPy array. Alright, you guys have to keep this calculation in mind. Alright, so whenever we have 2 rows and 3 columns, basically we are multiplying 2 into 3. We are going to have 6 elements. Alright, we'll be performing some advanced operations in the later stages. So you guys need to have this particular calculation on the tip so that you guys do not get a lot of errors later on. Right? Let's do another one. Say I have 4 rows and 4 columns. How many elements am I going to have? 16, right? 4 into 4. Let's do a last one. Say I have 10 rows and 5 columns. What's the total number of elements I'm going to have? Quickly comment in the chat box. Okay, it's going to be 50, right? So this is how you can generate random integers using this particular function. Alright, so moving on to our next topic, which is NumPy data types and typecasting. Alright, so NumPy data type is basically a function that tells us what kind of data types are stored inside the NumPy array. They could be integers, floats, strings, or complex numbers. Alright, so till now we saw how we can create NumPy arrays using inbuilt functions. Right, the first one was arrange, where we basically, if we were to implement that in Python list, we would use a for loop, right? We would give the start value, the stop value, and the step value, and then according to that, we would create a list. Similarly, in NumPy array, we can just do that using the arrange function. All right. Then we saw log space, we saw linspace, we saw some random functions like randn and just rand, right? We saw how they're implemented and their functions. All right. Now, another way to create NumPy arrays is manually. You can manually pass the integers or the elements that you want to be stored inside your NumPy array. So, for example, I want to create a NumPy array called ARR, and I will say NumPy array, and I will pass a list of all the elements that I want to be stored inside this array. Okay, so this is my array 1, 2, 3, 4, 5. All right. So if I change the data type of even a single element over here, so I basically converted 3 to 3.1, which is a float value. And now you can see all the elements in my array have been converted to a float. Alright. So as we already discussed, NumPy arrays do not allow multiple data types to be stored. So we're going to go ahead and check the type of our array. So as you can see over here, it's a NumPy array, right? Now another way we can create arrays is, say if I have a list called LST and I have a few elements in my let's say this is a string, then I have a few integers, and then I have some float values. Okay. Now, if I want this particular list to be converted into my NumPy array, all I have to do is say arr equal to np.array and pass my list in it. Sorry. Okay. So as you can see over here, all my elements inside the array are converted into a string format. Alright, so before we go ahead and check the data types of our NumPy arrays, here are a few common data types that exist. So the first one is int32. So these are 32-bit integers. So for example, the single digit numbers. Alright, then we have int64. So by default, whenever we store an integer, they are stored in the 64-bit format. It also depends on your machine specifications. So 64-bit integers are basically the larger digits. Then we have float 32. So again, they're the 32-bit floats. So basically 1.0, 3.14. But if we have a really large float value, it would be stored as float 64. And this is also the default data type of any float integer. Alright. So basically we have a lot of decimals over here. So it's going to be float 64. Then we have bool, which is basically boolean true or false. Then we have complex numbers like 1 plus 2j, 3 minus 4j. Then we have string, which is a Unicode string like hello 123, basically anything in double quotes. Alright, so that comes under strings. So these are the common data types that exist. So let's create an array containing only integers. So I have created an array using np.array, which consists only of integers. Alright, let's go ahead and print it. And now what I'm going to do is I'm going to check the data type. So over here it's int64. Alright, and now if I were to make even a single element over here a float value, my data type changes to float 64. Alright, now if I were to make it a string, let's see how it would get affected. So it's u32, basically specifying that it's a string data type. Alright, now another way that we can create NumPy arrays is while we are passing our list of elements, say I have 1, 2, 3, 4. Okay. Now I want these elements to be float data type. Alright. But if I were to print the data type right now, they're int64, right? They're integers. But if I want to convert them into float, what I can do is I can simply write d type, which stands for data type, equal to np.float. I can leave it at float, or I can also specify 32 or 64 according to, okay, there's a typo. So here my data type is float 32. I can also convert it to float 64 instead of float 32. Here, it's float 64. So I hope you guys are getting a basic idea. But if we were to do the reverse, say I have my float values over here and I want to convert them into integer 64, what do you think would be the result? Would I get an error, or would my elements get converted to int64? So let's check it out. So there's no error. Rather, my array has been converted to integer data types. So as you can see over here, the decimals are simply lost, right? So we basically round them up, and so if there was 2.6 over here, let's see what my array would look like finally. Yeah, so we basically just remove the decimals and pass the integers whenever we're converting float to integer. And we also saw that whenever we do not assign the data types, NumPy will do that for us automatically, right? Over here, you can see we did not happen to specify any sort of data type like float or integer. But if we go ahead and check the data type over here, it's going to be float 64. Alright, because by default our elements over here are float data types. So when we go ahead and check the data type of this array, it's going to be float. So NumPy will do that for us automatically. So we're done with data types. Now let's move on to typecasting. Alright, so typecasting is basically done using the function as type. Okay, so whenever you want to convert one data type to another, we use typecasting. So this is going to create a new array with the values converted to the other data type. It is not going to change the original array. Okay. So say for example, I have my array np.array, and I have my elements 1, 2, 3. So quickly comment your answers. By default, what is the data type for this particular array going to be? Okay. So if you guys have commented in 64, you guys are absolutely right, because if I go ahead and check the data type for this particular array, it's in 64, right? As we discussed, the default data type is always going to be in 64 or float 64, depending on integer and float values. Okay. So now I want to convert this particular array into float 64 instead of in 64. So what I'm going to do is I'm going to create a new array and say ARR, which is my previous array over here, dot as type, and I'm going to say np dot float 64. Okay. Now I'm going to print it. So you can see my integers have been converted to float values. Alright. I can also go ahead and print the data type. So you can see the data type is float 64. Alright. Similarly, we can convert float to integer. So let's convert this new array to integer 64. Alright. So here. So again, my new array 2 is again an integer. So I have successfully converted my float to integer over here. Now next we are going to look into something known as typecasting errors. So whenever we try to convert from one data type to another where typecasting is not possible, we get something known as typecasting error. So say for example, I have an array where my elements are 1, 2 and hello. Okay, so say all of these are strings. So even my integers over here are stored as strings. Sorry, this is going to be np dot array. Now I want to convert this particular array into an integer data type. So what do you guys think? Is it going to run successfully or is it going to give me an error? So let's go ahead and run it here. So invalid literal for int with base 10 np dot string hello. So over here we have hello, which consists of multiple characters and it cannot be converted into an integer or float format. Alright, so this is what is known as typecasting errors. So we cannot convert a string into integer or float. Is that clear? So now we saw how to create an array manually, how to check the data type and how to typecast those arrays, right? Now the next thing that we're going to look at is how to create a multi-dimensional array manually. Okay, when we were using the inbuilt functions, all we had to do was pass the number of rows and the number of columns that we needed in the array, right? But if we are creating an array manually, say np dot array, now what we have to do is we have to manually pass the elements in each row and each column that we want in our array, right? So this is going to be my row 1 and then I have my row 2, 5, 6. Okay. So as you can see over here, this is my first row and this is my second row. Alright. So I have 2 rows and 3 columns. 1, 2 and 3. I can also write it like this. So I hope this is more clear. So basically this is our column 1, 1 and 4. 2 and 5 is our column 2. 3 and 6 is our column 3. Alright, and these are our 2 rows. So if we go ahead and run it, right. So now why am I getting an error over here? Because these are 2 lists. Okay, so these are considered as 2 lists. I am allowed to pass only one list in my np.array function. So what I have to do is I have to place another square bracket so that this is considered as one list. Alright, now if I run it here, if I print my array, this is what my array is going to look like. Now I can go ahead and check the dimension of my array. So as you can see, this is a 2D array because it consists of rows and columns, right? You can check the dimension using ndim function. Alright, so there's another method where we can check the shape of our array using arr.shape. And you can see over here we have 2 rows and 3 columns. So the number of rows is always going to be the first argument or the first parameter in a tuple, and the number of columns is going to be the second one. Okay. The next thing that we can do with our array is we can check the size of our array. So the size of my array is 6. Now what this means is that I have 6 elements in my array. Now we already discussed it. We can calculate the number of elements by knowing the dimension. Now we already discussed this. We can calculate the number of elements of our array by knowing the shape of our array. So if we have 2 rows and 3 columns, it is just going to be 2 into 3, which is 6. Alright. Now the next one is checking the item size. That is the size of one element in bytes. Right. So we can do arr.item size. So basically each element in our array is taking up 8 bytes of memory. Alright. So this is how you check the item size. So these are some important properties of NumPy arrays. Alright. So moving on to the next topic, array reshaping, where we'll be learning about functions like reshape, ravel and flatten. Now what's the purpose of array reshaping? So say sometimes we want to change the shape of our array without changing the data. Alright, so say instead of 2 rows and 3 columns, I might want to have 3 rows and 2 columns. Right, so such array reshaping is done by the help of these functions, as you can see over here. So first let's look at reshape. Okay, so say I have an array and I have elements 1, 2, 3, 5, 6. Alright, so I have 6 elements in my array. So my reshaped array would use the function arr.reshape, where my elements would be distributed in 2 rows and 3 columns. Alright, so I can just say 2, 3. So initially my array looked like this, and then after reshaping, this is what it looked like. Alright, 2 rows and 3 columns. Now I can again reshape my reshaped array, where reshaped is my this particular array, right? 2, 3 columns. Now I want to reshape these two rows and 3 columns into 3 rows and 2 columns. So it's run successfully. If I print it, as you can see, I have 3 rows and 2 columns. Alright, so I hope reshape function is clear. Now moving on to the next one, which is Ravel. Okay, so Ravel is basically used to convert a particular array to 1D array. Okay, so whatever maybe the dimension previously, so we can just convert our reshape to array. Reshape to array is basically having 3 rows and 2 columns. So we are going to convert it into a 1D array. So as you can see over here, our array is converted to 1D again. The next one that we have is flatten. This is also going to convert your array to 1D array. Now what's the difference between Ravel and flatten? So basically Ravel is going to return a view, which basically means that any changes that you apply over here in this particular array are going to be reflected in your reshape 2 array. Okay, so basically this is going to return a view, whereas flatten, it returns a copy. So whatever changes you apply to the new array, that is the flattened array, are not going to be reflected in your original array. Okay, so let us just try changing something in the Ravel array. So say I want my first element, that is my element at 0th index, to be 100 instead of 1. Okay, so if I make this change, I'm going to print my Ravel array, and then after that I'm also going to print my reshape 2 array, which is basically the array that we converted to 1D. Alright, so let's see if both the arrays are changed or not. Yes, so as you can see, the first element of both the arrays have become 100. Okay, now if I try to use the flatten method, so I'm going to say flat equal to reshape 2 dot flatten, and I'm going to print it. So here, okay, now if I want the first element of my flat array to be 1 again, okay, now if I print reshape dot 2, reshape 2 array, so it's still 100. Alright, so any changes in my flat array are not being reflected in my reshape 2 array. Okay, so this basically means that we are creating an independent array over here, right? So I hope the difference between Ravel and flatten are clear, although their functions are the same. That is, both the functions convert any sort of array to 1D array, but whenever we use the Ravel method, we are basically returning a view of the original array, right? So let me just explain it over here in case you guys did not understand. So say I have my original array over here where, okay, 1, 2, 3, 4, 5, and 6. So basically I have 2 rows and 3 columns. Okay, so when I use the Ravel method, my array is going to look something like this. But this variable is still referring to this particular array. Okay, but it is only returning a view that looks like this particular array, right? It's basically returning a view that looks like one dimensional, but it is still referring to the original array. Alright, so whenever we make any changes, they are directly reflected in the original array. Make sense? But when we use the flatten method, we create an independent array where we convert the original array to a one-dimensional array. Alright, so whenever we make any changes, they have no zero connection with the original array. So it is completely independent. I hope the difference was clear. So moving on to the next topic on our list, that is arithmetic operations on arrays. Alright, so this is where we are going to perform the arithmetic operations. Again, NumPy lets you perform all the mathematical operations on entire arrays element by element without having to loop through them. Alright, so let me just create two arrays where my first array is going to be np.array and I'm going to have the elements 1, 2, 3. Similarly, I'm going to create another array np.array and I'm going to pass the elements 4, 5, 6. Alright, so let me run it. So the first operation is going to be addition. Now if I want to add these two arrays, all I have to do is print a plus b. And there, 1 plus 4, 2 plus 5, 7, 3 plus 6, 9. Alright, so I have my element wise operation and the result, the output is clear as well. Okay, so the next operation that I have is subtraction. So all I have to do is print a minus b and voila. So 1 minus 4 is minus 3, 2 minus 5 is again minus 3, 3 minus 6 is again minus 3. If I were to perform b minus a, we would get positive 3s here. Okay, moving on, we have division. So all I have to do is print a slash b and there. Okay, so it's basically 1 divided by 4 which is 0.25, 2 divided by 5 which is 0.4 and 3 divided by 6 which is half 0.5. Okay, so next one that we have is multiplication. So print a star b there. So 1 into 4 is 4, 2 into 5 is 10 and 3 into 6 is 18. Alright, easy enough. Now over here we perform normal division, right? And our answer was in float. But if we want to perform integer division, all we have to do is print a double dash b. So this is going to give us integer values, right? Okay, wait. It's supposed to be b slash slash s. Okay. So when 4 is divided by 1, it is going to be 4. When 5 is divided by 2, it is going to be 2. The roundup of 2 point, it's going to be 2.5, I guess. I'm not sure. I've not really done the multiplication. So next one is 6 divided by 3, which is again 2. Alright. So you can use double slash for integer division, whereas single slash for normal division. Then next you have modulus, which basically gives you the remainder. Okay, so all you have to do is print a mod b and you get the remainder. So when you divide 1 by 4, so let us get the remainder where b is divided by a. So when you divide 4 by 1, your remainder is going to be 0. When you divide 5 by 2, your remainder is going to be 1 because 2 2s are 4 and 1 is going to be the remainder. And since 6 is completely divisible by 3, our remainder is going to be 0 again. Alright. And then our last mathematical operation that we have is exponents. So this is basically the power. Okay. So all I have to do is print a double star b. Or I can just do every element raised to the power 2. Okay. So basically I'm squaring the array a. Alright. So it is going to be 1, 2 2s are 4. and 3 to the power 2 is 9. Okay, so as you can see, this is our output. So these were the element wise operations. Alright, so that was all about the mathematical functions. Now let's move on to our next topic, which is universal functions, or also known as U-funcs. So NumPy basically comes with many built-in math functions that work element by element, and these are called U-funcs that we just discussed. So for this particular section, I'm going to create another array using np.array and pass my list as 1, 4, 9 and 16. Alright, let's run it. So my first universal function is square root, which is written as np.sqrt. Alright, so let's go ahead and implement it. So all I have to do is print np.sqrt square root and pass my array as a parameter. Alright, so I want you guys to comment quickly what's the square root going to be for this particular array over here. 1496. 1 is going to be 1, 4 is going to be 2, 9 is going to be 3 and 16 is going to be 4. Let's see if that's the answer. Right. So you can see this is the answer, but it's returned in float data type. Alright. So moving on, the next function that we have is exponential, which is nothing but np.e to the power exp. Sorry, np.exp, which is also written as e to the power x, where x is any integer. Alright. So let's go ahead and implement it. So I want to print np.exp and say I want to print the exponential of only 1 and 2. Okay. So I'm going to pass it as a list, these two particular elements, and that. So e to the power 1 is 2.7 and the remaining decimals, whereas e to the power 2 is 7.389 something. I hope that's clear. So these are somewhat very basic mathematical functions that we will be using most of the time. So it's very important that you guys know the syntax and how to implement these functions, right? You can always go ahead and look them up online, but again, that's very time consuming. So it's particularly important that you guys remember the syntax somewhat, right? So the next one is sine function, which is nothing but np.sine. Okay. So say I have a few angles where np.array is equal to 0, np.pi. np.pi is nothing but the pi, right? So it's written as np.pi and then np.pi by 2. And then what we're going to do is we're going to print np.sine and pass angles as a parameter. Alright. So the sine of 0 is 0, sine of pi is 1. So you can see the sine of 0, pi by 2 and pi. Alright. So this is your resulting array. So this was all about the inbuilt mathematical functions. Now we'll move on to a very important topic, which is known as indexing and slicing. Alright. Now for all those who are not familiar with the concept of indexing and slicing, let me quickly tell you guys using a list. So say I have a few elements in my list. Now if I want to access the first element of my list, which is this, all I have to do is note down the indexes of these elements. Now indexes are something that represent the value at which these elements are stored, right? So this is what my indexes are going to look like: 0, 1, 2, 3, 4. Note that the indexes always start from 0. Alright. So if I want to access this particular element, all I have to do is look up the index of this particular element. Now I know that my element is stored at index 0. So all I have to do is access my index 0 and this would give me the result 1. Alright. Now this is normal indexing. There's something known as negative indexing as well. Alright. Now negative indexing basically starts from the last element. So this is going to be -1. Note negative indexing starts with -1 and not 0. Alright. So this is going to be, our last element is always going to be -1. And then we are going to count backwards: -2, -3, -4 and -5. Alright. Now if I want to access the last element, I can either say element at index 4 or I can say element at index -1. Now both of these are going to give me the value 5. Alright. So this is something known as indexing, where you refer to the indexes and access one particular element according to the index. The next thing that we have is slicing. Slicing is where you try to access a piece or a slice of your list or array, right? Now say if I want to access the first three elements of my list, all I have to do is access 0, 2, 4. Now why have I used 4 over here? Because I want the first, sorry, I'll be using 3 over here. My bad. I'm really sorry about this. Yeah. This is my starting index. This is my ending index. Okay. And the ending index is never included. So this particular array is going to give me the output 1, 2 and 3. The first three elements of my list. Okay. 0, 1 and 2. 3 is not going to be included in my output. Alright. Now if I want to access the last three elements of my list, all I have to do is -1 to -4. Right? Because I want the last three elements of my list. So I'm going to do -1 to -4. Now another thing that I have to do here is I have to give a step value that is -1. That is, I have to tell the computer that I want to subtract 1 from the starting point to reach -3. Alright, because by default over here, as you guys must have noticed, the step value is going to be 1. That is, 1 is going to be added to the starting value until it reaches the end value. Alright, so basically we're running a loop over here. So over here I will get the values 5, 4 and 3. Alright. If I were to not include the step value as -1 over here, my output would have been just 5. Let us quickly run it and see. Alright. So say I have my list 1, 2, 3, 4, 5. Okay. Now I want to access the last three elements, that is 3, 4 and 5. So what I'm going to do is -1, 2, -4. Okay, I am not including the step value over here. So let's see what's the output here. Oh, it's empty. So it's not including the last element as well. So as you can see, I've created my list over here. Now, if I want to access the last three elements of my list, that is 5, 4 and 3, all I'm going to do is pass -1 as my starting index, -4 is as my ending index. And right now I'm going to skip this step value to show you guys that my output is going to be 0. Like that is an empty list. Alright. So I'm not even going to access repeat. So I'm not even going to get my last element in my output. Now if I include the step value as -1, here you can see 5, 4 and 3 is my output. Alright. So this is basically how indexing and slicing works. I hope you guys got a basic idea. Let me show you guys a normal slicing as well. So basically I want to access all my elements, but I want to access them skipping one value from them. So basically I'm going to give my step value as 2. So I want the first element, the third element and the fifth element. So let's see how this looks. So as you can see, I've got my first, third and fifth element. Okay. Now let's apply the same thing for our NumPy arrays as well. Alright. So I'm creating an array, np.array, and I'm going to have my elements. Alright. So let us quickly see the indexes first. So this is going to be index 0, 1, 2, 3 and 4. Alright. So we have 0 to 4 indexes. Now if I want to access my indexes 0, 2 and 4, that is 0, 2 and 4, what is my syntax going to look like? So let's go ahead and slice it. So I'm going to say from starting to ending, but my step value is going to be 2. So as you can see, 10, 30 and 50. Okay. So I hope I'm making myself clear. Over here, I could have passed 0, 1, 2, 3, 4. Yeah. So I could have passed 0 and left this blank because I want this to be included as well. So, but instead of that, I'm going to leave this blank as well. So by default, this is starting index, that is 0, and this is the ending index, that is the length of the array. Alright. So this is how you can slice your NumPy arrays. Now let's look at negative indexing. So let's say I want to access my last element. All I'm going to do is, so it's giving me np.in6450 as the output, correct? But if I say print, so 50 is my output. That is the element at index -1. Similarly, you can go ahead and try negative indexing with other arrays and other elements. Okay, you can go ahead and play around with it. The main, the important thing is that you understand the logic behind it, right? And I hope I've explained the logic pretty well over here for both negative indexing, slicing, and negative slicing. All right. So we have already looked at slicing over here. We've looked at negative indexing. Now let's go ahead and perform multidimensional slicing. All right. So I'm going to go ahead and create a matrix. I'm going to call this 2D array a matrix, and it's going to look like this. So I'm going to have 3 columns and 3 rows, 4, 5, 6, and 7, 8, 9. Okay. Now I need to convert this entire thing into a list so that I do not get any error. So that I do not get any errors. Let me run it. All right. So now say I want to access the first 2 rows of my matrix. How am I going to do that? So in order to do that, all I have to do is print matrix and my row 0 and 1. All right. So I want my first row and my second row. So I'm going to say row 0. So this is my row 0, this is my row 1, and this is my row 2. I do not want the second row, so I'm going to have my stop value as my second row. Alright. Again, the indexing is going to start from 0. So this is our row 0. Alright. So this was about my rows and I want all my columns. So I'm simply going to pass 0 to 3. That means I want my 0th column, my first column, and my second column. Alright. So instead of this, what I could have done is just passed a colon. So let me see here. 1, 2, 3 and 4, 5, 6. Let me explain it over here. So I have a matrix 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. This is column 0, column 1, column 2. This is row 0, row 1, row 2. Alright. So basically this is what my matrix looks like. Now I am saying that I want to access this particular section of my matrix. So over here I want my row 0 and 1 and I want my column 0, 1 and 2. Alright. So over here my starting index should be 0 and my ending index should be 2. Over here my starting index should be 0 and my ending index should be 3 because I want my second column as well. Alright. So whenever we are accessing all the elements of a particular row or column, all we are doing is using the colons. We have used this feature when we were performing slicing as well. Alright. So this is basically what we have done over here. Now we can try some other elements as well. Say I want to access these 4, that is 5, 6 and 8, 9 elements. So what I'm going to do is I'm going to print my matrix and I'm going to say that I want my row 1 and row 2. So I'm going to say row 1 and I'm not going to pass any value here because I want my last row as well. Alright. And then I'm going to say I want my row 1 and 2. So again, I'm going to pass 1 colon nothing. Let's print it. So I've got 5, 6 and 8, 9 as my output, which is exactly what I wanted. Alright. So I hope you guys are getting a basic idea about indexing and slicing in 1D arrays and 2D arrays, and I am 100% sure that you guys can go ahead and perform it in 3D arrays as well. Alright. So let's move on to our next topic, which is index arrays and np.take. So index arrays are also known as advanced indexing. Okay. So let's quickly see what it is. So instead of filtering with true or false, we can directly pass positions or indexes to get specific values. Alright. Okay. So let's look at another method called np.take, which is basically a built-in function to perform indexing or slicing. So whatever indexes you want to access from your array, all you have to do is create a list of those indexes. So I'm going to use this particular array. Okay. So I want to access my indexes 0 and 2. Alright. So I have defined them in a list. So now all I have to do is print np.take, pass my array and the indexes that I want to access. Okay. So as you can see over here, at index 0 I have 10 and index 2 I have 30. Alright, so you can use mp.take to perform the same operations. Moving on with our next topic, that is iterating with nd iter. Okay, so in case you want to loop through the NumPy arrays, you cannot use a for loop, but rather you can use something known as nd iter. So it's going to let you loop over each element regardless of which shape it is, right? It could be a matter, it could be a 2D matrix, a 3D matrix. You can easily loop through it using nd iter. Okay, so I have an array np.array and it's going to be a 2D array having 2 rows and 2 columns. Okay, so let me run it. So all I have to do is for x in np.nd iter my array, and I have to print x and equal to, so that it gets printed in the blue line. Alright, so you can see these are the elements of my 2D array over here. Alright, so you can use nd iter, or another feature or method that you can use to iterate or loop over your array is nd enumerate. So over here, using this, you will get both your index value plus your value of the element value. Alright, so I'll use the same array. Okay, I'll use the same array, and I'm saying for ind, which is my index, and x is my value or the element, in np.nd enumerate my array, and I'm going to print my index and my x. Alright, so at index 0, 0, that is first row, first column, I have my value 1 and so on. Alright, so you can easily understand this. So moving on to views versus copies. Again, this is a very important topic. Okay, so we already saw that when we create a view, the original array is going to be affected, whereas whenever we create a copy, our original array is going to remain unchanged. Alright, so let's see how we can create a view. So if we have an array, let's create np.array. Okay, first I'm going to create a view. So my view is going to be array 1 to element. Let me print my view. So it's elements 2 and 3. Alright, now if I try to change my view, let's say I want my first element of view to be 200 instead of 2. Okay, let's check my view. It's array 203. Now if I try to print the original array, it has also been changed, right? As you can see over here, instead of 2, I have 200. Now let's try and create a copy. Okay, so in order to create a copy, all I have to do is say arr 1 column 3, that is elements 2 and 3 dot copy. Okay, now over here my array is going to look the same as what it looked in a view, but over here if I say my first element needs to be 2 again, over here it's changed, but if I print the original array, the element remains unchanged. Alright, the values are same as before. So this is the difference between view and copy. We had covered it theoretically, but now we have also seen the practical implementation of the same. So moving ahead, let's look at a very important mathematical concept in matrices, or whenever we have more than one dimensions in an array, something known as transpose. So we're going to look at transpose of a matrix. So say I have a 3 by 3 matrix containing values A, B, C, D, E, F, G, H, I. Okay, so this is a 3 by 3 matrix. Now what transpose basically means, so transpose of a matrix is basically a new matrix created by interchanging its rows and columns. Alright, so if this matrix is denoted by A, my transpose matrix is going to be denoted by A dash or AT. Alright, so this is going to be the transpose of my matrix. Now what interchanging rows and columns basically means is, if I want to transpose my matrix, so this is what my transpose is going to look like. So let's see how it is done using NumPy in our notebook. Okay, so let's create another array, np.array. Okay, 1 comma 2 and 3 comma 4. So you can see 1 and 2 are spread row wise, and 3 and 4 are the other rows, whereas 1 3 is first column and 2 4 is the second column. Now if I go ahead and print arr dot transpose, you can see my rows and columns have been interchanged. Alright. So now 1, 3 is spread row wise instead of column wise, and 2, 4 is spread column wise instead of row wise. Alright. Moving on to the next topic, swap axes. What this means is we swap two specific axes in a matrix. Alright. So I'm going to consider this particular array itself. Let me just copy it. Okay. Now let's quickly see the shape of my array. So arr dot shape. Okay. So it's 2 comma 2. So I need to change this into, okay, let me add another axis to it. Okay. So now it's 1 comma 2 comma 2. Alright. Now if I want to swap an axis, I'm going to say np dot swap axis, and I'm going to pass my array, and I'm going to say I want to swap my 0th axis with my first axis. Okay. Now I'm going to check swap dot shape. So now you can see these two axes have been swapped. It was 1 2, now it is 2 1. Alright. So basically you can choose over here which axis you want to swap. That's the only function of swap axis. Alright. Now let's look at some other functions like concatenation. So concatenation is basically when you join multiple arrays. Okay. So let us quickly look at concatenation. Okay. So say you have array 1 of 1 comma 2 and you have array b 3 comma 4. Now you want to concat these two arrays. That is basically you want to join them. So you can say, so that your result basically looks like 1, 2, 3 and 4. Alright. So in order to achieve this result, all we have to do is, if we had the plus sign, remember our element wise operation is going to take place. That is, if we simply perform a plus b, if that is what you guys are thinking, it's completely wrong, because our result is going to look like something like 4 comma 6. Okay, if we do a plus b, we've already seen that in the addition operation. So in order to do that, what we're going to do is, let me just create the arrays. Okay, so let me run it. Now, in order to combine these two arrays, all I'm going to do is concatenate, and pass both my arrays and then print my combined array. Okay, so my combined array looks something like this. Now, there are other ways to combine these arrays. Now, what if I want to combine these arrays not like this, but rather something like 1 comma 2 and 3 comma 4, and I want my array to look like this. Okay, so in order to do that, there is something known as V stack or vertical stack. Okay, so this is where you can understand, this is how I understood. So say if I have two arrays a and b, they must be having, okay, let me call it a1 b1. So they have these particular elements, okay, c b. Okay, and array b looks something like, now if I want to perform vertical stack on these two arrays, my output is going to look something like this. Okay, so my final output is going to look like a b c d. I'm not going to focus on the brackets right now. I'm more focused on the output p q r s. Okay, so basically this is how my output is going to look like. Let me just go ahead and implement it. So I have my array 1 nt dot array, and I'm going to pass a comma b, c comma b. Okay, I think I have to put them in quotes. So instead of that, I'm just going to replace them with numbers itself, and my array 2 is going to be, okay, so these are my two arrays. Now if I perform vstack, which is np dot vstack, and pass array 1 and array 2, you can see this is what my output is going to look like. Now similarly, similar to vstack, there is an other operation called hstack. Okay, now vertical, remember vertical is like this, where your two arrays are going to be stacked like this, whereas horizontal stack, remember it as the horizontal line, where your arrays are going to be stacked like that. Basically they're going to be concatenated. Alright, so in case of horizontal stack, my output is going to look like this. Okay, so it is going to be a comma b, c comma d, okay, p comma q and r comma s. Okay, let us quickly perform h stack. So if I were to print np dot h stack and pass both my arrays, you can see this is my output, just as we discussed. Okay, so basically it's going to be concatenated or joined horizontally. Alright, so I already told you the easy way how you can remember this. Whenever we're talking about vertical stack, all you have to do is imagine a vertical line, and then imagine the two arrays following that vertical line and finally combining. Whereas in the horizontal stack case, you imagine a horizontal line and imagine the two arrays following the directions and combining. Okay, so that's all about a horizontal stack and vertical stack. Now, if you don't want to particularly call H stack or V stack, what you can do is just call stack. Okay, and now this stack function is first going to take your arrays, that is A, B, and then it is going to ask for your axis. Okay, now always remember, axis 0 means row wise, whereas axis 1 is column wise. Okay, so this is something that you will have to remember. So say I print np.stack, I pass my arrays and I give my axis 0, which is basically going to be performed row wise. Alright, so axis 0 means rows. So whenever we're going to stack our rows, they're going to be stacked vertically. Whereas if my axis were 1 over here, my arrays would be joined column wise. Okay, let me just change this to 1. So our axis can only be 0 or 1. Okay. So this was all about joining or combining two arrays. Now let's look at the opposite function of that, that is splitting the arrays. Okay, so this is my array. Let me just print it. Okay, so this is what my array looks like. Okay, now if I want to split my array into two equal parts, all I'm going to do is print np.split arr1 and I'm going to say two parts. Alright, so this is my array 1 and this is my array 2. If I say I want to split it into three parts, I get an error because there won't be an equal division if I go for three parts. But if I go for four parts, you can see I get four different arrays. So in order to avoid error, you will have to do some prior calculations. Okay, you need to make sure that your array is eligible to split in those many parts equally. Alright. So if we perform edge split on our array and we say we want to split it into two parts, this is what our array is going to look like. Alright, so it's basically split into two parts. We've already discussed edge split is going to be performed this way and vertical split is going to be performed this way. So similarly, you can perform V split as well. You just have to pass the array and the number of splits you want to perform. Okay, you need to make sure that that number satisfies the basic requirement, that is the array is able to divide itself into equal parts. Alright, so moving on to the next topic, that is repeating and tiling. So first we'll look into repeating. So the repeat function basically repeats each element. Alright, so say I have an array over here that contains the elements 1, 2 and 3 and I'm going to perform the repeat operation saying np.repeat and I'm saying I want to repeat my array twice. So if I print it, you can see each element is repeated twice. Okay, so if I repeat it thrice, this is what my array is going to look like. Now the other operation is tile. Okay, now this is going to repeat my whole array. Okay, so I can simply say print np.tile array twice. Okay, so 1, 2, 3 and 1, 2. Alright, so this is all about repeat and tile. Then we have some aggregate functions. Okay, so aggregate functions are basically used to summarize the entire array. So say for example, you want to find the total, the average or the maximum element or the minimum element. Now in case of Python list, normally you would have to loop through the entire list and perform these operations. But NumPy arrays come with inbuilt functions. So say for example, this is my array. Okay, and if I want to find the sum, all I'm going to do is print np.sum and pass my array. Alright, so I have the sum of all my elements. Similarly, I can find np.mean, that is the average. So my average is going to be 2. 6 divided by 3. Alright, then I can find my median. So my median is 2 again, that is the middle value. So 1, 2 and 3. Then I can find the standard deviation, np.std. Okay, and similarly I can find the variance. This is basically the square of my standard deviation, and standard deviation is basically how spread your data is, your numbers are. Okay, then we can also find the minimum number or the minimum value on in my array. So my minimum value is 1 and the maximum value is 3. Alright, now if I have a 2D matrix and I want to find the sum across any one axis, I have some axis based operations that we can apply along any row or column in a 2D array. Okay, so say I have a matrix np dot Okay, let me just see if I have a matrix already. Okay, so I have this matrix already. So if I want to find the sum across only my columns, okay, so what I'm going to do is print np dot sum, and I'm going to pass my matrix, and I'm going to say axis is 1 because I want it across my column. So since my axis is 1, the sum of this particular row is 6, then over here it's 15, and over here it's 24. Now similarly, I can find row-wise operations as well. So 1 plus 4 plus 7 is 12. Okay, so this way you can do your row-wise or column-wise operations as well. Then next we have cumulative operations. Okay, so these are basically for calculating a running total. Okay, let's see how. So here I have my array 1, 2, 3. Now if I want to print the running sum or the cumulative sum of my array, I will just say mp.comSum, pass my array, and you can see the sum of my first element is 1, then sum of my first element plus my second element is 3, then sum of my first element plus second element plus third element is 6. Okay, so this is how a running total or a cumulative sum is calculated. Similarly, you can also calculate a cumulative product, saying np.comProd and pass my array. So 1 multiplied by nothing is 1, 1 multiplied by 2 is 1, 1 multiplied by 2 multiplied by 3 is again 6. Alright. Now moving on to conditional based choices. Okay. So first we are going to look at where. So say I have my array over here 1, 2 and 3. Alright. So I'm going to call my result variable, and I'm going to say np.where array is less than 2. I want to print low, and if my array value is greater than 2, I want to print high. Alright, so let's print my result. So here I have my result array saying low, high, high. Okay, so over here my value is less than 2, so I have printed low over here. Whereas over here these two elements are greater than 2, so over here we have high. Alright, so again this is the string format, and this is how it's represented. So the next feature is argwhere. So this basically gives the row column positions for 2D arrays wherever your condition is satisfied. So this is my array over here, and I want to find out wherever my elements are greater than 20. Alright, so it's telling me at index 1, 2 and 3 I will find my elements greater than 20. So at index 0, I do not have my elements greater than 20. But what if I change my condition to 0 over here? So you can see I have my index 0 also in the output. Alright. So let's move on to advanced conditionals using np.logical and logical OR. Alright. So this is my array, and now if I want to get values between 15 and 35, all I have to do is, let's create a variable mask and np.logical and arr greater than, that is my array, greater than 15 and array less than 35. Alright, so let's print mask. So over here it's false, over here it's true, that is 25, it's greater than 15, and 35 is again not less than 35, and 50 is again greater than 35. Alright, so you have false over here. Alright, so this was an example for a 1D array where we just had 3 elements. Now let's try for a more complex array, NumPy array. Let's take a 2D array. We already have a matrix over here. Alright, so now let me give a condition where I'm going to define np.argwhere, and I'm going to say wherever my elements in the matrix are greater than 5, give me the index of those particular elements. Alright, so you can see over here the first element that's greater than 5 is 6 over here, right? So the index of this element is row 1 and column 2. Alright, so you can see over here 1, 2. Then the next element that is greater than 5 is 7. So you can see over here 2, 0. Then we have 2, 1 for element 8, and value 9 we have 2, 2. Alright, so this is basically how np.argwhere works. Alright, it's going to return the row it's going to return the row column of your value wherever the values satisfy the condition. Alright, so moving on to our next topic, that is advanced conditionals using np.logical and logical OR. Alright, so basically we have and OR in Python, but in NumPy we use logical and logical OR. Alright. So in order to understand that, let me quickly tell you guys about this concept. So whoever is not aware about the concept of and or in Python, let me tell you. So say I have these particular values, alright? So now if I implement an and over here, that is a logical and between these two values, I'm going to get a 0. But if I implement a logical and between 0 and 1, I'm still going to get a 0. Between 1 and 0, I'm still going to get a 0. But whenever both my conditions are true, basically 0 stands for false and 1 stands for true. Okay, so basically over here what it means is if any one of my condition is false, my and result of that false and true condition is always going to be false. I am going to get a true only when both my conditions are true. But in case of or over here, we're going to get a result like this, because whenever we have any one statement, any one condition true, our result is going to be true. Alright. So this is basically what logical and logical or mean. Okay. So first let's go ahead and look at logical and. So we have an array. Let me just print my array. Okay. So this is my array initially. So what I'm going to do is I'm going to get my values between 3 and 6. That is, I want 4 and 5. So all I'm going to do is np dot logical and I'm going to say ARR greater than 3, comma, my array should be less than 6. Alright. So if I run it and if I print my mask, so over here I get my false, 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 true, true for 4 and 5. Now if I say ARR here, so I get my values 4 and 5. Okay, just like we intended. So this was the implementation of logical and. Now moving on to logical or. Okay. So over here, I want all the values other than 4 and 5. Okay. I want to skip these values and I want all the other values. So what's going to be my logic over here? Let me create my mask variable again. So I'm going to say np dot logical or, and I'm going to say my ARR, that is my array, should be less than 4 or my array should be greater than 5. So let me run it. Okay. So you can see for 4 and 5 I'm getting a false. Now if I try to fetch these values, so wherever I'm going to have a true in my array, those values are going to be printed. Alright, so you can see 100, 2, 3 and 6. Okay, so I hope the implementation and the logic behind logical and logical or is clear to you guys. So before we move on to our next concept, let us quickly go ahead and summarize the concepts or the important functions that we have covered so far. Alright. So the first one is Boolean mask. That is basically we want to select the values based on true false conditions. Alright. So here you can see we have created a mask variable. So once we get our array of true or false, we simply use that particular array to index the original array and get the elements that are desired. Alright. So we saw how we use the Boolean mask array to select the values based on true false conditions. Then we also saw np.take, which basically performs the operations of indexing and slicing. So it basically fetches the values at given indices. Then we have np.non-zero. Okay, so this gets the positions where the array values are non-zero. Alright. So let me create an array having, sorry, I have to say np.array 0, 1, 2, sorry, 5, 0, 5. Okay, so this is my array. Okay. Now what I'm going to do is print np.non-zero and I'm going to pass my array. So you can see these are the indexes where my elements are non-zero. Alright, so at index 1, at index 2 and at index 4. Alright, so the non-zero function is clear. So it's basically going to get you the positions where the array values are non-zero. Alright, then we saw np.where. So basically the where condition is going to get us the indices where the condition is true. But we already saw that one limitation over here is we can only pass two conditions, right? So we already saw the syntax where we say np.where and we give a condition and we tell, so if the condition is true, this particular operation gets performed, otherwise the other operation is performed. Alright, so we can only have two conditions over here. Alright, So pick from A, else pick from B. Then we have np.argware. So this is where we get the row column positions of matched values. Okay, we already saw this. And then lastly, we have logical and logical or. Alright. Okay, so basically we are done with all the inbuilt functions that exist in NumPy. So now we'll be moving on to a very important topic, that is broadcasting. Okay, so what exactly is broadcasting? So broadcasting basically means stretching the shape of smaller arrays so that they match the shape of bigger arrays. So whenever we're doing an operation like addition, multiplication, subtraction, any kind of mathematical operation between two arrays, and one of our array is smaller as compared to the other arrays, so broadcasting is basically going to automatically stretch the smaller array to match the shape of the bigger array. Alright, so basically, as a result, you will be able to perform these operations between those two arrays. Alright. So before we go ahead into the implementation part, here are three very important rules that you should know when you are going for broadcasting. Alright. So always remember that NumPy is going to compare the shapes of the arrays from the end, that is from right to left. Okay. So if we have two arrays, they are going to start from the end. So the first rule is, if the shapes are equal, they are compatible. Alright. So if we have two arrays that have the same shape, we do not need any sort of broadcasting to be implemented. They will be compatible directly. But if one is 1, it can be stretched to match the other. Now what this means over here is, so if we have one array like this, 1, 2 and 3, and the other array is just a single number 5. Alright. So say over here, I want to add these two arrays. Now over here, what NumPy is going to do is, it is going to perform broadcasting, and this particular array is going to look like this. Alright. So over here, initially this was a scalar array, but over here you can see this has become a 1D array. So if we perform this operation, it is going to look something like this. So rule 2 and rule 3 are related. If we read it just like that, it might not be very clear. So let us go ahead and understand this with another example. So say I have an array whose shape is 3, 1. Alright, so basically over here we have 3 rows, say 1, 2 and 3, and 1 column. Alright, so this is what my array looks like. Then I have another array who has a shape 1, 3. Alright, so this array is going to look like 1 row and 3 columns. Alright. Now, if we were to perform broadcasting between these two arrays, and say we perform some mathematical operation like addition, subtraction, multiplication, any sort of operation between these two arrays, our final array, our resultant array, due to broadcasting, would have a shape 3, 3. Alright. So basically, after broadcasting, this is also going to be 3, 3, and this is also going to be 3, 3. And that is how we get a resultant array that will have a shape 3, 3. Alright. So say for example, I have an array over here. Now what's the shape of this array going to be? The shape of this array is going to be 3, 1. Alright. So basically it's going to have 3 rows and 1 column or in each row. Alright. And then I have another array that looks like 1, 2 and 3. Now the shape of this particular array is going to be just 3, right? Because it has 3 elements, right? It's not a 2D array, it's a 1D array. So whenever we have to write the shape of a scalar dimensional array, we write it like this, 3 comma, okay? We leave it blank. But now due to broadcasting, this particular element will look something like 1, 3. So basically we're going to consider this as 3 particular columns, and this is 1 row. Alright. Now after stretching these two arrays, our final array is going to look like 3, 3. Okay, it's going to have the shape of 3, 3. So according to rule 2, whenever any one of the array has 1 in its shape, it can be stretched to match the other array. Alright. Now let's look at another example where one array has the shape of 2, 3, and the other array has the shape of 3, 2. So why any operation is not possible between these two arrays? Because neither of these arrays have the shape of 1 in any particular row or column. Alright. So I hope the rules are clear. So if the shapes are different and not 1 or equal, then broadcasting cannot be done. So this is the only case where broadcasting cannot happen. So say if shape of B was 1, 2 or 1, 3, then broadcasting could have happened between A and B. But if the shape is 3 comma 2 where 1 is not there, then any operation is not possible and broadcasting will not take place. You will get an error. Alright. So now let's look at some real life examples where broadcasting is used. So say you have a grayscale image stored as a 2D array. Alright. Now you want to increase the brightness of the image by 50. So let me create a 2D array of the image np.array, and so this is what my image array looks like. Alright, and I want my brightness to be image plus 50. Okay, I want to increase it by 50. Now if I print brightness, you can see it has been increased by 50. Overall my array has been changed. Alright, so over here 50 was broadcasted from a scalar digit to a array similar to this. Alright, so let's also check the shape of this 2D array. So it was 2 comma 2. So basically 50 was distributed in a 2 comma 2 matrix and then it was added in the image. Alright, so this is basically what's happening behind the scene that NumPy doesn't really want us to get bothered with. Alright. So that was all about broadcasting. I hope you guys got a basic understanding of the rules. The second and third rule are very important. If you guys did not understand it, you guys can go back and watch that particular section again. So moving on to the next topic, which is vectorization. Okay. So we already saw vectorization is basically when we replace the loops with array operations. Alright, we already saw array have numerous inbuilt operations that perform the mathematical operations directly, right? It could be sum, minimum element, maximum element. Any sort of operation that we want to perform on the list through loops can be done on arrays with a single function. That is known as vectorization. Now, why this is possible? This is possible because of NumPy being run on the compiled C code in the background, right? So it's basically much faster than Python as well. So now why are we looking at vectorization again, since we have already covered it in detail in using all the functions? Another important property of vectorization is, say I want to create a new function. I want to do something different that the inbuilt functions are not able to do as yet. So what I can do is I can write a function and I can convert that particular function into a vector. Basically, I can vectorize that function. So let's see how. Okay. So we are going to use here np.vectorize. Okay. So this is going to convert a regular function to be applied on an array. Alright. So I hope this is clear. So we'll go ahead and create a simple function. I will not do anything complex. Say I just want to create a function where I want to square all my elements. Okay. So all I will do is create the function. Now what I'm going to do is I'm going to create a variable vfunc, which is basically vectorized function, and I'm going to call np.vectorize and I'm going to pass my function. Okay, so this is my array and now all I have to do is print vfunc and pass my array. Okay, so you can see my array has been squared. All the elements have been squared in my array. Alright. So now you saw how you can basically convert any normal function into a vectorized function, but vector functions are to be used only when you want to apply a custom function to every element, and it is good for readability as well. So these are basically the benefits that you achieve when you're using a vectorized function. But there are some disadvantages as well. Okay, so it's not faster than a loop. Okay, basically you are going to pass your array into that function and the entire process is going to be performed. So it's not comparatively faster to a loop. The only thing it does is it makes your syntax cleaner, but it is not going to improve the speed like a real vectorized NumPy function or a NumPy array function. Alright. So if your purpose is not to increase the speed, you can go ahead and create vectorized functions. But if your motive is to increase the speed of your program or your code, then you should prefer the built-in NumPy functions like np.sqrt, np.exp that we just discussed. Alright. So now we'll move on to the last part of our course, which is dealing with missing values. Okay. So basically, whenever you have a data with you, okay, it could be any particular data. You will be having, say, let's say I am creating a house price prediction model. Okay, I'm going to have features like number of bedrooms, bathrooms. I'm going to have the location of the property. Okay, I'm going to have a number of features. All right, features are basically the columns in your data set. Okay, so whenever I have a data set, there are going to be some features where I am not aware of what data is over there. Okay, so basically that's called a null value. Okay, so whenever you're dealing with a data set, there are going to be cases where you do not have the complete data in your data set. What I mean by that is maybe you have uh, some data like this. So now whenever you see null written, that means that particular data is not available. Maybe the person forgot to update it. It could be any reason. Okay, so what do you do when you are in a situation like this, when you have some data and some data is missing? So this is where NumPy comes in the picture. NumPy is going to help you deal with all these missing values in your data set. Alright. So the very first feature that helps you deal with missing values in NumPy is np.nan. Okay. Nan basically stands for not a number. Okay. So this is used to represent the missing or undefined value. Okay. So let us see how it's implemented. So I have an array over here where my data looks something like 1, 2, np.nan 4. Okay, so you can see over here nan means not a number, means the value which was supposed to be here is missing. All right, then we have other functions like np.inf, sorry, minus np.inf. Okay, see, these basically represent the positive and negative infinite values. So they often appear where in cases like division by zero or overflow situations. All right. So I'm going to write positive and negative infinites. Okay. So again, instead of np.nan, you can just write np.inf. Okay. So I'm not going to go ahead and create an array separately. Rather, I'm going to jump to the next step, that is when you check for the special values. So here you can check if your array has any nan, inf or negative inf using special functions like np dot is nan, np dot is inf and np dot is finite. Okay, used to detect any sort of null value, infinite value or finite value. Okay, so let's go ahead and see how it's implemented. So let me create an array first that has all these criteria checked. Okay, so first we're going to use is nan. All right, so I already have an array over there. So all I'm going to do is print np dot is nan and I'm going to pass my array a. So over here you can see at index 2 I'm getting a true value. That means at index 2 over here my value is nan, that is not a number. Okay. Similarly, I'm going to create other arrays like np dot array and I'm going to have values like np dot none, np dot inf. Let me pass this in a list. So now over here I'm going to check for np dot is inf and pass my array. So I'm getting true at position 2, that is index 2 over here np.inf. So over here I'm not going to be made aware of any null value or not a number value. Okay. So if I want to find out null value as well as infinite value, what I can do is I can use np.logical or and I can say np.na, sorry, is nan. So first we looked into these functions, what nan did, what inf did and what negative inf did, right? And then we saw how we can find these null values or infinite values in our arrays. Now once we have found these values, the next step would be to replace or remove these values. So how that can be done? That can be done using np.nan underscore to underscore now. Okay, so let me create a new array and let me pass array b. So if I print my new array, so as you can see over here all my values have been changed. So basically the null values are going to be replaced by 0. The infinitely large values or infinite values that are positive are going to be replaced with a large number, whereas any negative infinite value is going to be replaced with a negative large number. Alright, so this is what np.nan to num does. Okay, so let me just write over here, remove not a number or infinite values. Alright, so this is what it does. So this is it for this video. I hope you guys got a basic understanding of NumPy and were able to get some insights out of this video. So keep practicing NumPy, and we'll be also doing a video on pandas. So stay tuned and see you in the next video.